Hi class, so today we will be doing a little experiment here with wedges, and as you remember from our notes, wedges are two inclined planes and put together, and they are used most commonly to part something. So basically what we're going to do is we're going to part these pieces of wood, and we're going to take a look at the initial effort that it takes on our spring scale to move that. It's going to be a little bit more difficult to, it's not going to lock out for us today, so we're going to have to kind of maybe take a look at it as as the numbers are changing, but we want to see what the effort is whenever we are first trying to get it to move, because that's going to be a good, I guess, example of how it is less effort when we use a longer wedge. But the first thing we want to do is we do want to figure out the mechanical advantage of our wedges. Okay, so we have this long wedge here. It is our first wedge, and we're going to need to measure it. Okay, so because we need the length and the height. So we notice right here it is 40 centimeters. We're going with the red number on the bottom there. 40 centimeters. And we have 4 centimeters. So we have 40 centimeters by 4 centimeters. And if you remember, to figure out the mechanical advantage, all you have to do is take the slope length, okay, which is 40, divided by the height, and we have a mechanical advantage of 10. Pretty major mechanical advantage there. We have never really had one quite that high. So that is the mechanical advantage. Okay. Now let's take the mechanical advantage for this one. Now, one thing I am doing is, rather than using the whole wedge here, I'm actually going to stop the measurement here. And the reason I'm stopping the measurement there is because I want the height of our two wedges to be the same, so that we can see the difference in mechanical advantage of, so if you look right there, you can see that, let me see if I can bring that a little closer. If we look right here, you can see that at the top of this black line, we have 4 centimeters. And now we will measure down from our black line, and we will get 12. Okay. If you notice there, it's a 2 after the 10, so 10, 11, 12. So our slope length divided by our height, and as we said, we're going to keep those in there. Or keep that at 4. So our slope length was 12 divided by our height of 4 equals 3. That's probably a math problem you could do, but we like to double check everything on our calculator because we do not want to have human error, which is something that I want to mention today. Is there are two other kinds of error that we can be aware of when we're doing our experiments. One of them is, one that we've already talked about, is friction. And friction can definitely cause error. And that's why a lot of our homework problems and things like that very much discuss situations in hypothetically frictionless. So a lot of our homework problems are in the hypothetical situation where there's no friction, but in real life that is not generally the case. So the next thing that, and we've sort of talked about this several times, is using a calculator and things like that so that we don't make human error, okay? We don't want to make a human error on our mathematics that's going to mess up our experiment. So that's why I always tell you, go ahead if you don't know the answer and work it out on your calculator. So with those measurements that we just got and using our calculator so we do not have any human error, okay, then we can go ahead and put those numbers into our box. So wedge A was 12 by 4, right? And we knew that that makes the mechanical advantage 3. And wedge B, a whole lot longer, it was 40 by 4, which makes our mechanical advantage 10. Okay? And when we do our experiment here, we are going to hopefully be able to see that the effort is less with our pull scale when we are pulling to get these first moving. That's what we're kind of looking for today. We're not looking to pull it clear in. We're basically looking to see how much it takes to just get it moving. Okay, and we will notice that with our longer, thinner wedge, it should take a whole lot less. So now that we have those mechanical advantage, let's go ahead and see if we can't fill in those last 2 blanks on that first part of our experiment page that says force needed. So, alright, here we go. The first thing we're going to do is we're going to kind of open up our 2 pieces of wood here, and to do the experiment with our block A first, we're going to move our block A kind of onto our board here. Okay. We're going to get our string in block A and keep block B's string out. Okay. Just have block A's on there. Put that down. Slide it back to just the tip of it is in the beginning there. We're actually going to hook it down with our 2 little rubber bands here. See our 2 little rubber bands? Now hook our screws down. Okay. And looks like we are ready to go. So, and once again we're going to have a 0 there. And this is the other reason I wanted to discuss error, is because I don't want to have a mechanical error. If I don't start out with 0, then I'm going to end up with a mechanical error. So, I'm going to zoom us in here a little bit so we can watch and see. This is our bigger one, and as it's starting to move, we can see it is over 2. Okay, let's try that one more time. Put just the tip of our wedge in there. I want to give you a chance to see it. Okay, and again we want to start out at 0. There, you can notice that there's a whole lot of difference from here to here. So we don't want to have mechanical error by pulling wrong. Here, it doesn't pull right. We always have to have it pulling straight on. So we'll pull it back here just a little bit so it is at the beginning again. And we want to make sure we are pulling straight. Okay, so we'll hook it on here. It is at 0. Hook Stick it on here, and we want to watch for this first number. It's most likely going to be 2. And it's starting to move. So you notice it is 2 or beyond every time it starts to move just a little bit. Okay, so let's take that big one out. That thick, short wedge out. And we will put our thin wedge in here. Okay. Have it so just the tip of it is on. Get our rubber bands back on here. This is our longer one here. Tighten up our string just a little bit. Okay. And then we'll be able to pull this one. So, and again, we don't want any see, if we would start now, we would have mechanical error because it is at 0.04 instead of 0. So we want to clear that out. Okay, it is at 0 and it's good to go. There we go. Put it back to pounds. That was what it was in there. Okay, let's see. Boy, it pulled right off the bat there. I wasn't even ready for it. So let's slide it back here again. Alright. Clear it out. And try to keep it in our screen there. Okay. And we'll go ahead and pull. It is much, much easier to pull. So let's do that one more time so you can get a good look at it. It doesn't even approach 2 when it is pulling. So let's take a look again. Let's clear it out. Make sure it is 0. And we'll look one more time. I don't ever see a 2 showing up there at the beginning. So we can see that there is less effort. If we think about it, and this isn't on pounds today, so it took 2 point something pounds, you know, so 2 pounds. We're not going to worry about the decimal point today because we know that it took 2 pounds, better than 2 pounds, to move the thick block, and it took 1 pound to move, or not block them, sorry, the thick wedge, and it took 1 pound to move the long thin wedge. So the effort that it took, the force that it took to move our block A was 2 pounds, 2 plus pounds. It actually took over 2 pounds, right? There was always a point there. So it was 2 plus pounds, and what it took to move our long skinny one was 1 pound. Okay, so the next section on your experiment page will be with the next video.